In this video, we're going to go over linear first order differential equations. And again, this is ODE, ordinary differential equations. It is not partial. So we're going to identify when we have a linear differential equation. We're going to define and determine integrating factors for linear differential equations, and we're going to solve some application problems. So our first order linear differential equation in standard form can be written like you would expect a line to be wrote. We have the slope, we have an x part and a given part, and then we have a y part. So this is nothing new in terms of linear equations. The way we write it in differential equations, it is x prime of t plus p of t x of t is equal to q of t. Now, if q of t is equivalent to 0 or equal to 0, then we call this a homogeneous linear equation. So if we're trying to determine whether or not these are linear or nonlinear, it needs to look like this. It needs to be x prime of t, a function of t with some p, x of t, and q of t. So our first example here, we know that t is not squared. We have an x of t, and our q of t happens to be 0. So this is a linear homogeneous system. So the first one is a linear homogeneous ODE, not system, just an ODE. Now for my second example, we know this is not linear, not because the t is squared, but because we have the sine of x. Now sine makes this a nonlinear because this is a function of x, where I've got it as sine, and that of course is not linear. So this is not linear. And then my last example here, we have y prime is equal to 1 over 1 plus e to the y. Again, this is not linear, not because of the structure necessarily, it's because we have e raised to the negative y. So this last example is also not linear. Something to note, if a linear first order differential equation is homogeneous, in other words, we have q of t is equal to 0, so it would look something like this, x prime plus p of t x is equal to 0. This is what we call a separable differential equation, and it can be wrote in the form of dx dt is equal to negative pt, which means this is equivalent to g of t h of t. And the general solution of these homogeneous systems can be wrote as x of t is equal to e raised to the negative integration of p of t dt, or in other words, 1 over e raised to the integration of p of t dt. Or as x of t is alpha e raised to the pt, or equivalently alpha divided by e raised to the p, and this is a capital P, where it is the antiderivative of p of t. So then x of t must be alpha e to the pt. Now this comes from our previous section 1.2, page number 18. When we're trying to solve a linear differential equations, we can separate if it's possible and then solve. We can multiply both sides by a positive function, provided it's positive, without introducing any new solutions, if this helps us. So how do you find a function mu of t that makes a linear differential equation integratable? Well, it's actually sometimes very simple and straightforward. So if I were asked to solve this differential equation, x prime plus 2x is equal to e raised to the negative 2t sine of t, then one of the things I can do is multiply both sides by e to the 2t. Now the reason I can do e to the 2t is, first of all, e to the 2t is a positive function. It's always, exponentials are always bigger than 0, so it's a positive function. And when I do that, I'm going to get e to the 2t, x prime, plus e to the 2t, 2x, is equal to. Now when I multiply e to the 2t multiplied by e raised to the negative 2t, the exponents are added, and so that's going to give me e to the 0, which is just 1, so then I have the sine of t. Now if we think about the fact that this here, this left side of the equation, is really d dt xe to the 2t. And you're like, how did that happen? Well, remember, when I take the derivative of x, that becomes x prime e to the 2t. When I take the derivative of e to the 2t, this is implicitly, this is going to give me 2 e to the 2t multiplied by x. So that whole left side is d dt of xe to the 2t. And this is equal to the sine of t. Now, if we integrate both sides, so I'm going to integrate d dt of x e to the 2t, and I wrote x, e to the 2t, t dt is equal to the integration of the sine of t dt plus c. Now we know the left side, that the integration of d dt of e of x e to the 2t is just going to be x e to the 2t. On the left-hand side, excuse me, the right-hand side, I'm going to get negative sine, negative cosine, integrating this, negative cosine of t plus c. To get x all by itself, so this is really a function of x, a function of t in terms of x, I'm just going to divide everything by e to the negative 2t. So this is negative e raised to the negative 2t cosine of t plus e raised to the negative 2t times c. And that is my answer. Now, sometimes it's not going to be that easy. So we need to find this mu of t. It's called the integrating factor. Now we know that mu of t must satisfy e raised to the pt dt. And also u prime of t minus p of t, mu of t, has to also equal 0. So we know that mu prime of t must be equal to p of t mu of t, which means if we go back to our linear equation here, x prime of t plus p of t, x of t, q of t, of course we're not talking about a homogeneous. Homogeneous are much easier. We have mu of t, multiply both sides by mu of t. We get mu of t, x prime of t plus p of t, x of t is equal to mu of t, q of t, which gives me, by the product rule, so this is what we have, and by the product rule, we know mu of t, x prime of t plus mu prime of t, x of t. Taking the derivative or the integration of this side, which gives me this, and finally here's where I am. X of t is equal to 1 over mu of t, the integration of mu of t, q of t, d of t, plus c. So, the first thing we want to do to solve linear first-order differential equations, provided it's not homogeneous, is to put it in standard form. So here it is in standard form. Now we want to make sure that we divide the coefficient x of t if it's not 1. So if there's a coefficient on x prime of t that's not 1, we want to divide every term by that to make that coefficient to be 1. Then we're going to find the simplest possible antiderivative for p of t for that coefficient, capital P of t, for the coefficient of p of t. We're going to let mu of t equal e raised to the antiderivative of p, or in other words, cap p of t. We're going to multiply both sides of the equation by mu. Do not forget to multiply that q of t by that mu as well. Then we're going to integrate both sides with respect to t. Don't forget that constant. And then when we finally get done, we're going to divide both sides by mu of t to obtain the explicit solution. And you're like, holy smokes, what are we doing? Well, let's go ahead and go through this process with a couple of examples. And I've gave you the slope field for this so you can see what the slope field looks like. So first of all, we ask ourselves, is this in the right form? And the answer is yes. Remember, the form is going to be y prime plus p of x. This is a lowercase p, by the way. That's not a cap p. Multiplied by y is equal to q of x. Now, a good choice for lowercase p of t is this 2 because that's the coefficient on that y. And I also see that my y prime is isolated. There's nothing besides y prime. There's not a 2 or an x or anything like that. So then a good choice for p of x, lowercase p of x, is 2. And then q of x would of course equal the 2e to the x. Now my integrating factor, I call this I of x. My integrating factor I of x is e raised to the integration of that p of x dx, which is the e raised to the integrating factor, or the, excuse me, not integrating factor, e raised to the integration of 2 dx. When I integrate 2 dx, that's just going to give me e raised to the 2x. So now I've found my integrating factor. I also know that my general solution must satisfy y is equal to 1 over my integrating factor multiplied by the integration of my integrating factor q of x dx plus c. So my y must be equal to 1 over e to the 2x, the integration of e to the 2x multiplied by my q of x, which is 2e to the x. This is my q of x dx. So then y is equal to 1 over e to the 2x, the integration of 2 e to the 3x dx plus c. Don't forget my plus c. Almost got wild and crazy and forgot my plus c. So when I integrate this, I'm going to get 1 over e to the 2x, and then I'm going to have multiplied by 2 divided by 3, e to the 3x. Don't forget that, plus c. And so this is going to be equal to, distributing e to the 2x through, 2/3 subtracting exponents e to the x plus ce raised to the negative 2x. And that's what my y is equal to. So let's go ahead and take a look at another example here. So the first thing is I got to have it in the right form, and it's not. It should just be y prime by itself. So I'm going to divide each one of my terms by x. So that's my first step. So I have y prime is equal, not y prime, y prime plus 2x over y is equal to the cosine of x over x squared. Now I've got to pick a good choice for my p of x. My good choice is this. So p of x, lowercase p of x, is 2 over x. So that is a good choice for p. That tells me that q of x is going to be equal to the cosine of x over x squared, because that's my q of x. Now I know that p of x and q of x is continuous everywhere on the interval from 0 to infinity. Now that's because I want to have that positive function. Remember that positive function thing. Okay, so now I have to figure out what a good integrating factor is going to be. Well, my good integrating factor is going to be I of x is equal to e raised to the integration of 2 over x dx. Well, this is going to be e raised to the natural 2 times the natural log of the absolute value of x, and then no dx. And so this ends up becoming e raised to the natural log of x squared. Now the squared allows me to take off the absolute value symbols. And then we have this rule with the laws of logs, it just becomes x squared. So that's my integrating factor, okay? That's my integrating factor. So then if I go back to my original equation here and do like I did before, my y is equal to 1 over my integrating factor, the integration of my integrating factor, q of x dx plus c. Don't forget my parentheses here. That tells me that my y is going to be 1 over x squared, integrating x squared multiplied by, and I had cosine of x over x squared dx plus c. So y is equal to 1 over x squared. And you can see that my x squareds are going to cancel, leaving me the integration of the cosine of x dx plus c, which is 1 over x squared, the sine of x, plus 1 over x squared multiplied by c. So my general solution is y is equal to x raised to the negative 2 sine x plus c x raised to the negative 2. I could have left it like this too, by the way. I just think that that one's just a little bit nicer. Okay, let's look at my last example here, and same kind of thing. The first thing I want to do is I need to put it in the right form, so I need to isolate my y prime. So I'm going to divide everything by x. And so I've got y prime minus 1 over x multiplied by y is equal to 2, the natural log of x. A good choice for my p of x, here's my p of x, which is going to be 1 over x. That's a good choice for my p of x. I can choose negative 1 over x, and that's okay too. And then I'm going to have, actually, I'm going to choose negative 1 over x. The reason I'm going to choose a negative 1 over x is because I'm going to go back and say, remember how it's supposed to be like this, where I've got y prime plus p of x, y, q of x. So I'm going to let p of x equal negative 1 over x. This must be my q of x, so my q of x is going to be equal to 2, the natural log of x. And my integrating factor I of x is going to be equal to, just like before, I of x is equal to e, the integration of negative 1 over x dx, which is going to be e raised to the negative natural log of the absolute value of x. Now, we know that this then becomes e raised to the natural log of the absolute value of x raised to the negative 1. Now, we are assuming we're going to be working with a positive. That's my p of x has to be positive. So we know this is continuous on the interval from 0 to infinity. That's going to ensure that I have a positive, so I don't have to worry about taking the absolute value. So this is just e raised to the natural log of x raised to the negative 1, which means this is just x raised to the negative 1, or in other words, 1 over x. Bam. All right, so now I'm going to go back. And I am going to write y is equal to 1 over my I of x, and then multiplied by the integration of I of x, q of x, that's a q, believe it or not, dx, plus c, which is equal to 1 over x, so that just gives me x, the integration of 1 over x, and then multiplied by 2, the natural log of x, dx plus c. This is a nice u sub, so this isn't anything exciting. This is a nice little u sub. And because this is a nice little u sub, this is going to be x, and then 2, don't forget the 2 there, becomes a natural log of x, the quantity squared, divided by 2, plus c. Oh, don't forget that I would have had to multiply this c also by an x. I distributed that x through. And so I end up with x, the natural log squared of x plus c of x. And this is my y value. And that's it for this one. So not too bad. Notice how the process is the same over and over again. Now, the only difference between the previous one and this one is the fact that I now have an initial value, so I can figure out what c is. That's all it is. I'm still going to go through the same process. This is still in the correct form. It is y prime plus p of x, y. A good choice for p of x on this one happens to be 1, so that's nice. My q of x happens to be x. My I of x is going to be e raised to the integration of dx, which is just e to the x. My y is equal to 1 over e to the x multiplied by the integration of e to the x, and then x dx plus c. And I'm just going to cut to the chase and give you the answer. This is going to be a nice integration by parts, so make sure that you spend some time reviewing integration by parts. My final answer is x minus 1 plus 2e raised to the negative x. And that is my final answer when I get done. All right, let's go ahead and look at an application problem. This is a single compartment mixing problem. And what that means is that we're going to be taking some, quote, pollutant, and we're going to put it in a container. And the pollutant is going to be, quote, pollutant, is going to be entering this container at a fixed rate and also flowing out. Whatever fluid is flowing amount is also going to be flowing out. Not necessarily the same amount, but we also have a flow out that has a fixed rate. So like if you are mixing saline into pure water, and at the same time you're mixing the saline in, that the volume is not increasing, so we have this outflow. So the pollutant would be the saline. So the rate of pollutant per unit of time is equal to the rate in minus the rate out. So we let A of t equal the amount of the impurity at the compartment at some time t. V is the volume of the compartment. And so the A of t divided by V is the impurity concentrate of the tank. So in other words, dA dt must be equal to the inflow rate minus the outflow rate, where the flow rates are the products of the form of concentration multiplied by the volume flow rate. We're going to let R sub in and R sub out denote the flow rates in and out, and K sub n denote the impurity concentrate of the inflow. Then what we end up with is dA dt, the amount of the impurity with respect to time, the change in the amount of impurity with respect to time is equal to K sub n multiplied by R sub n minus A of t divided by V multiplied by R out. When Rn equals R out, the volume is constant. When Rn does not equal R out, then it's not constant. And when that happens, my volume is going to be the V naught plus Rn minus R out multiplied by T. So in other words, my volume could increase or my volume could decrease if my flow rates are not the same. So let me lock this again, because I hate it when it does that, when it rotates like that. So here's a couple of examples. A tank initially contains a solution of 10 pounds of pollutant in 60 gallons of water, so like saline. Water with a half a pound of pollutant per gallon is added to the tank at a rate of 6 gallons per minute. The solution is thoroughly mixed, and then it also leaves the tank at the same rate. Find the amount A of t of the pollutant out of the tank at any given time t. So we know that K sub n multiplied by R sub n must be equal to 1/2 a pound of the pollutant multiplied by its rate in, which is 6. It's the rate in. So this is equal to 3 pounds per minute. We also know the outflow rate, A over 60, multiplied by the R out, must be equal to A over 60 multiplied by 6, because my outflow rate is the same as my inflow rate. So this tells me that A over 10 is going to be A over 10 pounds per minute is going to be my outflow rate. Now my rate of the change in the pollutant at any given time is dA dt is going to be equal to the 3, that is my K sub n, R sub n multiplied together, minus my A over 10. Now we know that we can rewrite this differential equation as dA dt plus 1 over 10A is equal to 3. And you're like, why would I do that? Well, Now we know that this is a separable, not separable, but this is a linear differential equation. So we need to find the integrating factor. In this form, a good choice for P of x is 1 over 10. That means Q of x is equal to 3. That means I of x is going to be equal to e raised to the integration of 1 over 10 dx, which means this is e raised to the 1 over 10x. So now we found our integrating factor, and we can go ahead and find the general solution, and I'm just going to cut to the chase. My general solution of a of t is going to be equal to 30 minus CE, or excuse me, plus CE raised to the negative t over 10. I guess I'm using t's here, so I guess I should change this back to not p of x, but p of t. So let me just go back and change this. So p of t here, p of t here, p of t here. So q of t, p of t, I of t. And instead of dx and x here, it'll be dt. And this will be 1/10 t. All right, so that is my general solution right here. So here's my general solution. Now, we also know that the tank initially contains 10 pounds of pollutant at 60 gallons, so I can now figure out what my initial C is, and I'm going to put in 10 pounds of the pollutant at 60 gallons of water. Solving for t, I get A of t is equal to 30 minus 20 e raised to the negative t divided by 10. And this is my answer, given the fact that I have this initial value. Here is my last and final example. I have a tank that has a capacity of 3 meters cubed, or in other words, 2,000 liters, is initially full of pure water. At t equals 0, the salt with the salt concentration of 5 grams per liter begins to flow in. To take the rate of 10 liters per minute, we're going to mix this solution. It's going to be a well-mixed solution, and the tank is pumped out at the same rate. So we know, as before, that dA and dt is going to be equal to Kn multiplied by Rn minus A over V, R out. So we know that Kn is 5 and the R sub n is 10. So Kn multiplied by Rn is going to be 10. Multiplied by that 5, multiplied by that 5, which gives me 50. My initial volume is 200 liter or 2,000 liters, so that's 2,000. And my R out is the same thing as R in, so that is equal to the 10. So where I am now is I have dA dt is equal to 50 minus A over 2,000 multiplied by 10. Rearranging, I have dA dt, and then I'm rearranging this because I want this to be linear, plus 1 over 200a is equal to 50. Now, a good choice for P of t is 1 over 2,000. Q of t is equal to 50. That means I of t, my integrating factor, is going to be e raised to the integration of 1 over 200 dt, which is e raised to 1 over 200 multiplied by t. Doing my usual solving, I'm going to have A of t is going to be equal to 10,000 plus CE raised to the negative 1 over 200 t. Using my initial condition, which is at A of 0 is equal to 0, I'll be able to solve for C. And I get C to equal a negative 10,000. And so my final answer is A of t is equal to 10,000 minus 10,000 e raised to the negative 1 over 200t. And that is my final answer, that initial given condition. And that's it for this video.